Good afternoon, everyone. Today, I'm going to discuss a paper about NeuroCool dynamic thermal management of 3D for deep neural networks through customized prefetching. This paper is proposed by S. Pandey, Sidhu, and Pierre Panda from the Department of CSE. I'm going to discuss this paper and their paper algorithm, how the paper methodology should work, what would be their properly results of the paper, and first of all, my name is Shovik Das. Good afternoon, everyone. My name is Shovik Das, and I'm the passionate about exploring the optimization for memory solutions. So today I present this work as on NeuroCool, a thermal-aware memory management policy designed to address the challenges of running deep workloads on 3D data. So coming to the paper name is NeuroCool, Thermal Management of 3D Dynamic RAM in DNNs. I'm Shovik Das from Macau, MSc in Artificial Intelligence and Department of Science 2024 batch. And but before starting this thermal management of 3D dynamic RAM DNN, to understand what is a 3D dynamic RAM. So 3D dynamic RAM, 3D RAM. So first of all, I have to understand what is a 3D. So 3D RAM is a type of memory technology where multiple dynamic RAM layers are stacked vertically. So to improve the efficiency, capacity, and the performance, and unlike the traditional 2D dynamic RAM, which are arranged in single layer. So 3D dynamic RAM integrates the several layers of connected 2D layers. They are integrated and it becomes a 3D dynamic RAM. So they are the more performance than the 2D RAM. So it was mainly interconnected through the silicon wires. We call it TSV through silicon wires through TSVs. Okay. So this is the main basic idea of the what is the 3D RAM. So so coming to the next thing that we have to understand why DNN. So first of all, you have to understand that deep neural networks are computationally too much intensive because these have the several neurons and several hidden layers and several, output layers through several bias and several perceptrons they have. So it was computationally intensive work and requiring efficient memory systems. So however, we have the 3D dynamic RAM, but in a 3D dynamic RAM, a memory architecture using high performance DNN, and it faces some challenges like thermal hotspots. Like in particular, DNN layer should generate will generate some significant heat or it becomes some overheads. So it generates some significant thermal hotspot which degrades the performance of the and energy efficiency of the DNN. And this chapter mainly introduces that a policy or a technique called NeuroCool, a customized dynamic thermal management approach called a DTM, dynamic thermal management approach, designed to optimize the execution of the memory intensive DNN workloads. So we have to optimize that DNN workloads in the dynamic 3D. So there's a technique called NeuroCool. We'll discuss about that after that. So before understanding this DNN workloads and other NeuroCool things and their main algorithm, we have to understand the what is the main objective of this paper. So let us discuss the objective. So understanding the objective of the paper is that we have to minimize the cooldown period. First is we have to minimize the cooldown period. To minimize the cooldown period. To minimize the cooldown period. Have to minimize the cooldown period. Second objective is that maximize the DNN performance and efficiency by addressing the thermal and memory bandwidth issue. There are the two issues. One is the thermal and band issues, and second one is the memory bandwidth issues. We already know that in GPT-2 or BERT model is required maximum number of bandwidth. So we have to deal with the two things: the thermal issues and the memory bandwidth issue. And the third point is that the provide the application aware prefetching, like the, it depends on the application. So provide the application aware prefetching tailored to different layers and operations in DNN models. So these are the 3 points that we are mainly focused on this paper. So, so if I briefly discuss the objective of the paper is to address the thermal challenges associated with the running deep neural network inference on systems and they utilize the 3D stack dynamic RAM. The paper aims to the four things we already discussed. The three things: the main will reduce the thermal management overheats, that the overheats occurring. Number two is optimize the DNN performance, and third is propose a DNN new policy which is called the NeuroCool, and the fourth one is demonstrate the generalization and effectiveness. The paper is mainly seeks to enhance the overall feasibility of using general purpose CPUs with the 3D dynamic RAMs for high throughput DNN inference, making them more efficient and competitive without relying on your speed accelerator like GPU or anything. Now, so let's coming to the given diagram. This diagram, we can see in this given diagram there is a temperature graph and there is a time graph. So in x-axis, this is a time graph. Sorry, in x-axis there is a time graph and in y-axis there is a temperature graph. According to that, this is a C critical, a T critical. That means the critical temperature. If the temperature exceeds the T critical, we'll think as a this is a overheat issue. We have to deal with that. How to deal with that, we'll discuss about the later. So if we see in this area particularly, this is a zoom version of this area. The green line depicts that our the green line depicts mainly our default enable default prefetch. So if we see the green line, we can see the default prefetching maintain the higher temperature throughout the timeline. So although it does not oscillate as much as the disable prefetch, but it struggles to stay below at the critical threshold due to the aggressive prefetching and sustain the heat accumulation. So if we zoom that version, we can see that there's some kind of degradation of the temperature are there. And if we follow the other lines like the blue line, the blue line mainly it's mainly focused on the disable prefetch. Like the policy exhibits the frequent thermal spike. Like it's frequently thermal spike. The spike is too long. So with the temperature exceeding the C critical, T critical, like the critical temperature. So multiple times it decreases. So indicating the insufficient thermal management. So if we disable the prefetching, say insufficient thermal management will be there. And obviously the lack of prefetching causes the irregular heating and the cooling patterns are there. So leading the performance degradation. And let comes to the best thing like the red line. If we saw the red line is here. You can see that the red line is here, the red line. So if we saw the red line properly, we can see that, or you can understand that the custom prefetch strategy effectively keeps the temperature below the C critical, T critical for most of the execution. But it avoids the overheating by dynamically adjusting prefetching settings based on the workloads characteristics, showing a smoother and more controlled temperature profile. So this is all about the custom prefetch technique was discussed here. So if we saw the a zoomed view of this picture like this, we can see that the disable prefetch have the sharp drop in the temperature like 660 ms time. So sharp drop there. So it requires much time to recover their systems. And if we consider the green line and the red line, it's have the sharp drop, but it can recover it properly and in a particular time. So we can consider the other parts. So later we will discuss about this issue. So next. So if we saw the this area, this thing. So in that time, coming to the next slide, it's background on transformer models. Like there are two transformer models we are going to discuss here. First one is the BERT model, encoder based model, and the GPT is a decoder based model. So we can know that the transformer architectures are widely used in mainly NLP, like natural language processing, or two key models are stands for like BERT and GPT. BERT is an encoder based model and GPT is a decoder based model. So BERT is a bidirectional encoder representation from transformers, and GPT is the generative pre-trained transformer. So in GPT model, the GPT model is mainly perform matrix vector multiplications. Like there is a matrix and there is a vector multiplication will be occurred. So it's computationally much intensive than the BERT model, and for that, in case it's multiplication during the mark self attention, so including memory operation, it's required. And in GPT-2, it's also required the memory bandwidth requirements like higher compared to the encoder based model like BERT. So GPT models definitely needs the higher memory. So it's in that case it generates significant types of attention, self attention. So I think the challenges of managing 3D dynamics runs comes like multiple challenges comes. So like the objective of the NeuroCool, before understanding the objective of the NeuroCool, you have to understand that what are the challenges coming from that managing 3D dynamic RAMs. So if we coming to the challenges, there is two challenges are coming. Number one is a thermal hotspot. Number one is a thermal hotspot, like layers like self-attention layer or attention layer and a feed-forward operation generate significant heat. So in the 3D dynamic RAM, there is the one challenge is thermal hotspot, And if we consider the second challenge is like the high memory bandwidth requirement. Like GPT models require high memory bandwidth, so it's required the high memory bandwidth requirements. So there is two challenges coming to the GPT, GPT not mainly the GPT model and for the 3D dynamic RAM. So these two challenges are coming. So in that case, we'll using the objective new techniques called NeuroCool, and they are the objective of the NeuroCool, the goals of the NeuroCools too. So we'll discuss about that in the next slide. So coming to the next slide. So in NeuroCool, we can see that we mainly focused on two major things. Like first major thing is like customized prefetching, and the second is hybrid thermal management techniques. We also call this HYDTM. We also call this HYDTM. So there is a two techniques: the customized prefetching and the hybrid thermal management technique. So before understanding the customized prefetching properly, we can understand the what is the prefetching means. So prefetching is the process of loading data into the memory before it's needed. So NeuroCool dynamically adjusted the prefetch settings based on the type of DNN operation. So how it can understand, like there is multiple types of operations like linear GEMM, batch GEMM, feed forward layers and layer normalization. So according to that, it depends on the prefetch class. This may be high or very high. Maybe in linear GEMM it's very high. Maybe in feed forward it is disabled. So it be based on that it dynamically adjusts their prefetch settings. So we can see that there is multiple a diagram is showing here. So this figure mainly illustrates the prefetch settings used in memory systems. This figure is illustrated, and the key parameters like prefetch degree, prefetch interval, and prefetch stride. So the prefetch degree is like the determines the how the memory block. I mean how many memory blocks data are fetched at a time, like the prefetch degree. And the prefetch stride is that like the stride defines the spacing between the successive data block fetched during the prefetching. So this is the main things, and the prefetch interval is the time. This is the time between the consecutive prefetch operation for a particular epoch or for a particular iteration, like those things. So these are three main operations are given here. So after that, the purpose of these things is like these parameters are crucial balancing for performing the energy efficiency in memory intensive workloads. Like the higher prefetch degree, the optimal prefetch size and the prefetch interval is depends. Like the higher prefetch degree can reduce the memory access latency. If we decrease, I mean, increase the degree of the prefetch degree, so obviously the latency or latency memory access latency, but increases the energy uses, but the heat generation it also increases. But in the optimal prefetch stride, the ensures relevant data fetched without wasting the memory bandwidth. And in the prefetch interval, it determines how frequently prefetch occurs, influencing memory access patterns. So according to that, if we consider a one example, like the prefetch interval is 10 nanoseconds. Here, the prefetch stride is like 3, and the prefetch degree is 1. Like the stride means 3 means that the 3 blocks are consecutively sent, and it sends after the 3 blocks. And the prefetch degree is 1 means that one iteration, or like the how many blocks are sent, like the one block is sent for the prefetch stride 3 minutes after the 3 blocks. So like that this is going to be happen. So it is dynamically depends on the application on the other things. So I think mainly the figure is demonstrate mainly the how these parameters are can be tuned dynamically to adapt the varying workloads requirements. We can modify the prefetch degree and stride systems like NeuroCool. We can optimize the prefetch for specific workloads, balancing performance and thermal efficiency, obviously. So this is the customized prefetching techniques are mainly discussed. But we will discuss the main algorithm later on. But this is the main customized prefetching is discussed, and the hybrid thermal management technique is like it's like it monitors the memory temperature and workload phases, adjusting the prefetch and memory states according to the to three things. Like one thing is like reduce overheating. We have to reduce the overheating issues, reduce overheating. Second one, we can consider the balanced memory performance with thermal limits. To balance the memory performance according to with or according to, we can consider according to thermal limits, like thermal limits. So we can do both of the things. Okay. So this is the main overall idea of the paper. So let's come into the main thing, the algorithmic steps. So we'll discuss the algorithm in the next paper. Before understanding the algorithm, we have to give a glance of like what are the parameters we are using here? So discuss first. Like the first parameter is like the input parameters here. The first input parameters of T of CO2 in R minus 1. This is the first input parameter we are using. This is the temperature of memory ranks. An array. This is basically an array. So basically an array. This is basically an array representing the temperature of each memory rank, where NR is the total number of ranks. So after that we are using the TCRIT, T critical. This is a T critical, another variable. It is the critical temperature, the threshold at which the DTM should be invoked to cool down the system. So first the main thing, the security critic, and after that we are using another variable like AP, like this variable. This is the memory access parallelism. So we are using this memory access parallelism for an indicator how the parallel memory accesses during the DTM, I mean dynamic thermal management. So this is the memory access parallelism. After that we are using another parameter called LT. LT, another parameter called LT is a layer type. I mean layer type. So layer type means the type of DNN layer is currently executed, which affects the memory patterns. So like it may be a hidden layer or our input layers. Which input layer or which hidden layer is mainly depicts the layer of the DNN layer. So after that we are using the LF, another variable. So LF mainly calls the layer footprint, the memory footprint of the current DNN layer, which affects the memory uses and access patterns. After that we are using also TREC, T recovery. The mainly thing is the T recovery. So T recovery mainly is the meaning of the T recovery is the recovery temperature, the temperature threshold below which the memory can return to an active state to after the cooling down period. So if the temperature crosses the critical temperature, it goes to the that it shows that thermal management should be needed. And if the temperatures comes down to the T recovery, then they saying if the cool down period is going to happening, we have to stop that and we can do the normal execution process. We have to start the normal execution process. So this is the thing. So these are the some parameters we are going to use here. After that, there are some output parameters too. Like we have to change the color. Huh? Yeah. So there are output parameters too. So output parameters like the name like suggests. First is the rank state. Rank state. So rank state is minor minus 1. This is the rank state. The power state of each memory rank. I mean whether it is active or standby or cooling mode. So its rank state is just shows the answer. So this is the first output parameter, and the second output and the final output parameter is the config p. It's like CON. The config p is 0 to NC minus 1. So the core prefetch settings for the current execution, how aggressively memory should be prefetched based on the layer type and temperature or full footprint. So it's a config p. So these are the two output parameters, and the one global variables are present. This is called the p. We depicts by the p. We change the color first of all. Yeah, the global variable is P. The P selects the DTM policy. It's selected the DTM policy. This determines whether the system should apply the rank-wise, tier-wise, or all-tier-wise DTM policy based on the layer characteristics and memory bandwidth patterns. So it depends the DTM policy. It determines the DTM policy. Which DTM policy should we apply to the given parameters or given algorithm, given neural network or deep neural network. So this is the input parameters we will discuss about. Now coming to the main thing, the algorithm first of all. Here is our algorithm first of all. Okay, so we have to discuss this algorithm properly and understand how this algorithm works. Okay, so first input parameter we discussed, and the output parameter we also discussed, rank state and config p, and global variable we discussed the p select the DTM policy. First step is step number 1. Step number 1 is that this line TM, get the max rank temperature T. Okay, get the max rank temperature T. So this is the get the maximum temperature and saves to the TF T of M. saves to the T of m. This is the step identifies the maximum temperature of T of m from the list of temperature of all memory ranks. The memory rank is T of 0 to n minus 1. We already give the temperature memory rank. From it catches the highest maximum temperature and saves to the T of m. Simple thing. It saves the T of m. After that, if we see in the step number 2, if we see the T of m is greater than T of critical. That means the maximum temperature, wherever we have that maximum temperature is more than the critical temperature. That means we have to start the DTM policy. If the maximum temperature is greater than the T of critical temperature, the maximum temperature is greater than the system is considered to be heated and the thermal management needs to be triggered. So the system will proceed to the apply. You can see that if system will proceed to the heated and apply the HYDTM high thermal management and the TAP. That means hybrid dynamic thermal management technique and the TAP is temperature aware prefetching techniques. Those two things we have to apply, start or trigger those two things. In after that, in step number 3, we can see that. So in step number 3, we can see that system select the DTM policy, like select DTM policy AP. So select the DTM policy based on the memory access parallelism, how the memory access can be happening. So according to that, it selects the DTM policy in the P. So select the DTM policy, select DTM policy according to the AP. Like the AP means we already got that AP is a memory access parallelism. So accordingly, it selects the memory access parallelism. So high access parallelism may trigger the more aggressive DTM strategy, or such as cooling more tires at once, or while low parallelism may result in cooling individual ranks also. So this decision is made using the policy of selection function, like select DTM policy, which consults a table or a decision time to choose the optimal policy. So these are the things. Okay. So after that, so in step number 4, we can see that the DTM engine is now invoked, applying the chosen DTM policy P. So we are using that rank state. We are using that rank state. Rank state. The rank state, we use the obtain rank power state using the T critical and P. So the rank power state is obtained based on the current temperature, the memory ranks, and the selected policy. So this is the thing. The ranks are too hot. Example, the temperature exceeds the T critical. If the temperature is crossing the T critical or more than the T critical, it are placed in a standby mode to the cool down. Placed to standby mode to cool down. So this is the thing. It's rank state occurring. Rank state doing. So after then coming to the step number 5, we can see that in step number 5, config p, the output variable. We already got the rank state. After the config p output variable, we can see that config p is the second output variable. This is the number 1 output variable. These are the number 2 output variable. Config p. Config p doing what? Compute prefetch settings LT, TM and TF, L of F. So the parameter is passed is L of T, T of M and LF. So the tab manager, mainly the tab manager, computes the core prefetch settings config p based on the current layer type LT, maximum temperature and the layer footprint. So it is the given. So after that, in the 6th step, you can see the rank state. You can see the rank state. Rank state is changed according to set active on cooldown. So rank state is changed according to that. So rank state is first is changed by the set active on cooldown. So it's showing what after the initial cooling phase. So after the initial cooling, the temperature falls down the recovery temperature T recovery. So if the falls down the T recovery, the rank state is set to active state. So set to active state on cooldown T recovery and the P according to the P. So if the temperature in the first step, if the temperatures go up to the more than the T critical, the rank state shows that we need the DTM policy. And if the temperatures goes down to the T recovery, then the rank state shows that we are already cooled down. We have to start the process now. You can now generate the heat. So rank state shows that the set on active cooldown. So these are the two things. So those two output parameters you already got, rank state and the config p. So that in case in the 7th step, we're doing what? Return rank state and what? Config p. config p, rank state and config p. So the algorithm returns the final rank state and the computed code prefetch settings config p that should be applied on the next layer or maybe in the next epoch. This is the thing. The rank states mainly indicates whether the each memory rank is active or standby mode, and config p provides the prefetch settings for the core based on the current DNN layers or characteristics. Okay. So after that, we can consider that this is the main thing of the algorithm or main process of the algorithm works, how the algorithm mainly works in that NeuroCool process, NeuroCool mechanism or NeuroCool methodology. Okay. So coming to the next slide, like what are the benefits of NeuroCool? No, we can say that the NeuroCool benefits like the application specific optimization. So the application specific optimization. So like adapts the prefetch and thermal management strategies to specific DNN operations. So application specific optimization we can consider. So these are the benefits of NeuroCool. We already gone through the paper. The paper has also present that benefits of NeuroCool. Then first is application specific optimization, and the second one we got here like energy efficiency. Energy efficiency. So reduce energy uses by 47%. We can see that they reduce energy by 47%. Maybe it is in, I think I remember it is in a GPT model maybe. So in GPT model, reduce energy by 47%. And number three is faster execution. They reduce the execution time by 45%. This is the faster execution. Reduce the energy time by 45%. In the result, we already got that. Result table in that paper, we already have that the faster execution will happen, and this is the time by 45%. And the last one is the broad acceptability, like the DNN training tasks, the custom neural network architecture accelerator, integrated architecture, or the GPU systems. We can use this type of NeuroCool technique for that. So this is the benefits of NeuroCool, and if we discuss the future direction, so we can also call that the broad acceptability. After that broad acceptability, we can consider that the DNN training tasks we can consider, and in GPU systems we can use that NeuroCool techniques, and also the integrated architectures we also use that NeuroCool techniques. So there are several ways we can use the NeuroCool policy in the afterwards. So this is the main, main basics of the paper, or the main overview idea of the paper along with the algorithm. So if we come to the conclusion of the NeuroCool, we can say that the NeuroCool demonstrate the apply the application aware DTM policies significantly to enhance the performance and efficiency, to enhance the performance and enhance the efficiency also enhance the performance and efficiency of the DNN workloads by intelligently managing the memory operations and thermal conditions. And it sets a new benchmark on DNN execution on modern hardware-based systems like GPU or dynamic 3D RAMs, those things. So this is the main conclusion of that paper, and this paper is having the good feedback and also the good citation I touched on. And thanks for giving this opportunity for presenting review so much.